Hey everyone, Mr. Helk here. In today's video, we're going to be looking at multiplying vectors by scalars. By the end of this lesson, we should be able to multiply a vector by a scalar term, represent scalar multiplication graphically, and understand that multiplying by a non-zero scalar will change the magnitude and possibly the direction of the vector. Let's go ahead and get started. So, scalar multiplication refers to the multiplication of a vector by a constant, which we call a scalar, to give the vector with different magnitude. This is very similar to multiplying a number by a scale factor to increase or decrease its value in proportion to its original value. So, geometrically speaking, scalar multiplication achieves the following. Scalar multiplication by a positive number other than 1 changes the magnitude but not the direction of the vector. Scalar multiplication by -1 reverses its direction but does not change the magnitude. Scalar multiplication by any other negative number both reverses the direction of the vector and changes its magnitude. And we can see that here in some of these examples. In this case, this is the vector p. If I multiply by 2p, well, notice 2 is a positive number, so it's changing the magnitude, the length of the vector, but it's not changing the direction. Same thing here, 1/2 p, well, the scalar is 1/2, and 1/2 times the vector p is changing the magnitude, but it's not changing the direction. However, here with the vector -p, we have the same magnitude as p, we have the same length of the vector, however the vector is now moving in the opposite direction of p. So to continue, scalar multiplication can change the magnitude of a vector by either increasing it or decreasing it. Scalar multiplication by a number greater than 1 or less than 1 increases the magnitude of the vector. So again, if you multiply by a scalar that's bigger than 1 or less than -1, you increase the magnitude of the vector. But if you have a scalar that is between -1 and 1, so basically a fraction, you're going to decrease, or a fraction between -1 and +1, you're going to decrease the magnitude of the vector. And again, that was seen right here in 1/2 p. We had the scalar 1/2, which is less than 1, and that scalar of 1/2 decreased the magnitude of the vector p, even though it kept it in the same direction since it was a positive 1/2. So, the algebraic definition of scalar multiplication of a vector, so let's say the vector v has horizontal component vx and has vertical component vy. So the scalar multiplication by a scalar c is the product of each component of the vector by the scalar. So c times the vector v would be c times the horizontal component vx, and then c times the vertical component vy. We can also do the same thing if we have our vector represented as a linear combination of the standard unit vectors I, j, and k. It'd be the same basic process. If I multiply the scalar c times the vector v, then the linear combination version would be c times the horizontal component I plus c times the vertical component vy, j. And the same thing in three-dimensional space here. So let's see a couple examples here. So in this example, given that the vector u has components -3, 5, write the components and draw the vectors for vector u, 2 times the vector u, 1/2 times the vector u, and the negative vector u. So let's start with the vector u. Of course, we already know that the vector u is -3, 5. We can say that vector 2 times the vector u, well, let's just multiply the components times 2. -3 times 2 would give us -6. 5 times 2 would give us +10. So 2 times the vector u has components -6 and +10. Next, we'll move on to 1/2 times the vector u. So again, we'll multiply 1/2 times the components of vector u. So -3 times 1/2 would be -3/2. 5 times 1/2 would be 5/2. However, since we know we're going to be drawing the vectors on the coordinate plane, let's go ahead and just represent these as decimals, just to make it make a little more sense to us. So -3/2 as a decimal is -1.5, and 5/2 as a decimal is 2.5. And again, this will come in handy when we actually graph the vectors here in just a moment. And then lastly, let's go ahead and calculate negative vector u. We just take vector u, multiply its components by -1. This would give us, -3 times -1 is +3, and 5 times -1 is -5. So notice that I've already graphed them here. And one of the points that I want to stress is that our vectors do not have to have initial points at the origin. Remember that when we have vectors written in component form, like vector u here, these are simply the components. This says that this vector u has a horizontal component of -3, meaning the horizontal component is moving to the left 3, and has a vertical component of +5, meaning the vertical component is a +5 going up. So as long as the vectors that we draw on the coordinate plane have the correct components, it doesn't matter where in the coordinate plane that we place those vectors. So I've decided to place the original vector u right here. Again, notice it has a horizontal component of -3 right here and a vertical component of +5. 2 times the vector u should have a horizontal component of -6, which it does, moving to the left, and a vertical component of +10, which it does. I just decided to place it over here. You can place it anywhere as long as you have the correct components. 1/2 times the vector u has a horizontal component of -1.5. Kind of hard to see, but we can zoom in here. Again, horizontal component of -1.5, vertical component of 2.5, and I just decided to place the vector here. And then we have negative vector u, which has a horizontal component of +3 and a vertical component of -5. We can see that right here. Horizontal component of +3, vertical component of -5. Now, once again, notice that with negative vector u, because we multiplied by a scalar that was negative, this is essentially a -1, we have the same magnitude as vector u. You can see that these two vectors have the same length, the same magnitude. However, they are moving in complete opposite directions. Okay? All right, now let's talk about parallel vectors. So two vectors are considered parallel vectors if they have the same direction or exact opposite directions. Essentially, what this means is that if I have two vectors, if there is a scalar such that one vector is equal to a scalar multiple of another vector, then those vectors are parallel. Just to give some quick examples, let's say we had one vector is equal to 2 times the other vector. These would be parallel. Let's say we had one vector is equal to -1/2 times the other vector. These vectors would be parallel. As long as there is some scalar such that one vector is every component is a scalar multiple, the same scalar multiple of the other vector, then the vectors are parallel. So let's take a look at these examples down here. So we want to determine if each of the following vectors are parallel. So looking at vector A and vector B, we want to figure out, can I multiply one vector, each component of that vector, by some scalar multiple to completely get all the components of the other vector? Well, what I'm noticing here, I'm going to look at the first components of each vector. What could I multiply 2 by to get a -6? Well, I know 2 times -3 would give me -6. So now let's check it with the other component. If I multiply -4 times -3, I get a +12, which checks out. I get that right there. So it turns out if I multiply each of the components in vector A by -3, I get both the components of vector B, which means that vector A and vector B are parallel. So in writing, this is what we would say. We would say that vector B is equal to the scalar multiple -3 times vector A. And we can see that because -6, 12 is equal to -3 times the components to -4. And we just showed the math there. So again, since vector B can be written as a scalar multiple of vector A, vectors A and B are parallel. So I'm going to go ahead and say, yeah, parallel. Ooh, don't like that. I like the little shaded inbox. There we go. All right, let's try another example. Over here in the second example, we have a vector in three-dimensional space. We have vector C has components 4, 10, and 2. Vector D has components 2, -9, and 1. So let's try the same thing. I'm going to look at the first components in each vector. Looking at vector D, this has the smaller component. Is there anything I can multiply 2 by to get a 4? Well, yeah, we know 2 times 2 would equal 4. So I'm going to check the next component. Can I multiply negative 9 times 2 and get a 10? Now we know the answer there is no. We know that negative 9 times 2 is negative 18. So these two vectors could not possibly be parallel. The reason they're not parallel is because the same scalar multiple cannot be used to multiply all the components of one vector to get all the components of another vector. So in writing, I would say this. No scalar, that doesn't look like a C. Let's try that again. There we go. No scalar multiple could work. Or no scalar multiple such that vector C equals k times vector D. We'll call k the scalar multiple there. So these are not parallel. Okay. One more example. Ooh, don't like that. We know that. There we go. Okay, so one more example here. Let's try. We have the vector E is 6i minus 12j plus 24k. Vector F is negative 2i plus 4j minus 8k. I'm a fan of writing our vectors in component form, so I'm going to go ahead and write vector E. Let's get shape recognition off. Vector E has components 6, negative 12, 24. And vector F has components negative 2, 4, negative 8. So let's do our same process here. I'm going to look over here at negative 2, just because, 2 is a smaller number than 6. Is there a number such that I can multiply negative 2 and get a positive 6? Well, sure. Negative 2 times negative 3 would give me positive 6. So let's check negative 3 and multiply it to the other components of vector F. Well, 4 times negative 3 would be negative 12, so that works. Negative 8 times negative 3 would be a positive 24, so that works. So essentially, vector E is equal to negative 3 times the components of vector F. So these are parallel. Okay. So now let's talk about calculating the magnitude of a scalar multiple, of a scalar times a vector. So recall that the magnitude of a vector is simply you take the components of the vector, you square them, you add them together, and you take the square root. Well, we can very similarly calculate the magnitude of a vector multiplied by a scalar c. Let's go ahead and see what that would look like. So if we were to try to find the magnitude of c times vector v, well, this is what we would get. So we would have, let's go ahead and multiply c times these components on the inside. So we would have c times vx squared plus c times vy squared. Going ahead and simplifying, notice that since we have a c to the second power in each, I'm going to factor out c to the second power. This would give us vx squared plus vy squared. And since we're taking the square root, we know that the square root of c squared would be c. I'm going to go ahead and put absolute values around here. I'm going to talk about that y in just a moment. But we have the absolute value of c. And then notice that what we would have remaining is vx squared plus vy squared. But notice the square root of vx squared plus vy squared is the magnitude of the vector. So this would be the absolute value of c times the magnitude of the vector v. Now let's talk real quickly about why I put absolute value signs around the c. Remember that we're calculating a magnitude. Magnitude is always going to be positive. It's the length of the vector. Remember, if you have a negative, you're multiplying by, let's say, a negative scalar. The negative doesn't affect the magnitude, it's affecting the direction. And that brings up the next point right down here. The direction of a vector, c times vector v, is either the same or opposite to the direction of the original vector v, depending on whether the scalar you're multiplying by is positive or negative. If the scalar you're multiplying by is positive, so if the scalar is greater than 0, then c times vector v has the same direction as vector v. And if the scalar you're multiplying by is negative, then c times vector v has the opposite direction as vector v. So again, when we're going to calculate the magnitude here, we're not worried about the sign of c, because the magnitude is independent of the sign. Magnitude is a length. So it's the absolute value of the scalar you're multiplying by times the magnitude of the original vector. And let's see that in action here with an example. So we want to find if vector v has components -3 and 5, we want to find the magnitude of 2 times vector v. Well, using the formula that we just derived, we're going to take the absolute value of the scalar and multiply it times the magnitude of the original vector. So this would be equal to the absolute value of 2 times the magnitude of vector v. Well, we know the absolute value of 2 is just 2. And if I go to calculate the magnitude of vector v, that would be the square root of -3 squared plus 5 squared. This would be 2 times, well, let's see, -3 squared is 9, 5 squared is 2, or no, 5 squared is 2, 5 squared is 25. 25 plus 9 is going to be 34, so this is 2 square root of 34. Okay, so there's our magnitude of 2 times vector v, 2 squared of 34. And let's make a special little note here. Once again, let's talk about the direction. So note since the scalar we're multiplying by 2, we're multiplying by a scalar 2, since 2 is greater than 0, okay, since 2 is greater than 0, 2 times the vector v is in the same direction as vector v. Okay. So let's look at one last example to kind of bring this all home. We have vector v, which has components 2 and 4. We want to compute 1/2 times vector v and -2 times vector v. We're then going to graph all 3 vectors on the same coordinate plane, and we're going to compare the magnitudes of the 3 vectors. So let's start with 1/2 times vector v. Well, we're just going to take the scalar multiple 1/2, multiply to the components of v, which are 2, 4. So the first component, 2, times 1/2 is just going to be 1. And the second component, 4, times 1/2 would just be 2. Next, let's go ahead and look at -2 times vector v. Well, let's multiply -2 times the components of v. -2 times +2 is going to give us -4. And 4 times -2 is going to give us -8. So we get components -4 and -8. So what I've done here is I've gone ahead and graphed vector v here in black. Once again, remember that when you graph a vector, they don't need to start at the origin. Your vectors just need to have the correct components. So then I graphed vector 1/2 times vector v, which had components 1 and 2. I just decided to graph it over here. Notice we have horizontal component 1, vertical component 2. And then I went ahead and graphed -2 times vector v, which had components -4 and -8. I decided to graph it over here. So here's horizontal component -4. Here's the vertical component of -8. So let's look at the magnitudes. So once again, notice that, with respect to vector v and -2 times vector v, the magnitude from vector v to -2 times vector v, the magnitude doubled. And again, the negative sign only affected the direction. It didn't affect the magnitude, it affected the direction. Same thing over here between vector v and 1/2 times vector v. Notice that the magnitude got cut in half. So these scalar multiples certainly affect the magnitude the way that we expect them to, according to this formula.